Yes, thanks to the organizer for this nice workshop and also for giving me the opportunity of presenting some ideas here. So this is the outline of my talk. It's actually relatively simple. It contains just a bit more information with respect to the title, but yes, it's more a collection of things that have been scattered among different papers, and we try to collect them and to give them some order. So this quantum contextuality community grew a lot in the past year. So as we've seen also with the talks in these days, there are many different approaches, terminology, theories, and so sometimes it's difficult to somehow communicate also between these different communities or groups. So we try to kind of collect these ideas. Maybe we introduce even new terminology, I don't know. We try to collect these different ideas and to give some organization in this review paper. So I encourage you, so from some of you, and also for many other people that are not here, we already received some comments, suggestion, criticism on this. So I invite also all of you, if you have some time, or even to read just small sections or paragraphs that maybe are more relevant to your research. And if you want to discuss with us some of these things, so this is still on archive, is not published. So if you're interested in someone giving suggestion, yeah, I encourage you to do so. Also, I wanted to say that this topic is quite complex. So maybe some of the things I will say will sound a bit superficial. There are many more subtleties, but I hope in this short time I will be able to give you at least the main ideas of all the problems related to this experimental test of contextuality. Okay, so to start, let's start with the Cauchy-Specker contradiction. So we have this set of projectors in a three-dimensional space, or dimension d higher than 3. And contexts here are defined by a set of orthogonal projectors. So we can imagine you have P1 to PD, and they respect some orthogonality constraints. So if I have D orthogonal projectors, rank 1 projectors, they will be orthogonal for a different index. And then if I sum all of them, they will sum up to the identity. Okay, in Cauchy-Specker in particular, consider these 117 projectors in dimension 3. So what is the idea of the argument? They want to interpret each projection as a proposition. So they want to assign a truth value, let's say true or false, or 1 or 0 to all of them. And so in each context, they get some constraint on each context because of this orthogonality and completeness relation we've seen before. So in particular, not 2 of them in the same context can be true at the same time. And if I consider all of them, they cannot be all false. So there should be at least 1 true and all the other false. And the context here is this set of, let's call it jointly decidable proposition or orthogonal projectors. And we want our assignment to be context independent. Okay, so what is the result? They try to assign this truth value to this proposition associated with the projectors with the 2 constraints we just seen, and they show that this is impossible. So they get some sort of logical impossibility proof. So it's some like sort of logical contradiction. So it's not obvious from here to pass from a logical argument to, let's say, a statistical one and test it in the lab. There are some examples of this. We have seen some of them in many of the previous talks. So one possible abstract definition could be the following. We have a set of measurements, and among these measurements, so there are possible subset of them that define context. So context means that we can have a joint observation over all the variables in the context, and this will give a probability distribution. And non-contextuality amount to the existence of a global probability distribution such that this context observation is just the marginals. Okay, but this is not the only one, the only definition. So also there's a definition by Speckens that involves no joint measurements, no marginals, and so on. So I would like maybe to first give some sort of comparison between these two. I also want to point out that so far we discuss an operational approach. So what do we have to measure in the lab? How, what are the contexts? How can we identify them? Also, the idea of context-independent, let's say, value or measurement or variable implies that we have to identify, let's say, the same measurement or the same variable in different contexts. So how can we do that? Okay. So in order to understand the different approaches, it's good to go back to this Cochen-Specker contradiction we just seen and try to interpret in two different ways. So the first one is what we call the observable perspective. So let's say we have P1, P2, and P3, and these three operators, let's say, represent three commuting observables. So each one is a measurement with effects P and 1 minus P, and I can measure them together. And the joint measurement will be the P of M with effects P1, P2, P3. So the idea of contextuality is that I can measure the same observable in different contexts. So I can measure P1 together with, let's say, P2 prime and P3 prime, or in other contexts, and I want to assign a value to this observable P1, which is independent of the joint measurement I'm doing. Another perspective is based rather on effects. So I can say that P1, P2, and P3 are the effects of joint measurement. And so the same effect P1 may appear in different measurement, for instance, with P1, P2 prime, and P3 prime. So this is my opinion, but you may disagree with that, but I will say that this observable perspective is closer to the original formulation of Cochen-Specker that spoke about, let's say, simultaneously decidable proposition or commeasurable, observable, and things like that. While on the other hand, this effect perspective is somehow closer to the way the Cochen-Specker theorem became popular. So it's something about orthogonal vectors. You have a basis and you want to assign 1, 1, and 2, 0 to this basis and so on. But at this level, let's say, since we are dealing with ideal measurements, there is not much difference between two. So we can, in both cases, we can obtain this Cochen-Specker contradiction. Okay. And this is the same thing, just in more abstract term. And I'd say that observable perspective, in the observable perspective, the basic object of contextuality are observables and their compatibility, or let's say joint measurability relation. And a context is defined by a set of compatible observables. Non-contextual hidden variable theory assign value, which is independent of, let's say, which joint measurement each observable appear. Okay. In this effect perspective, the basic objects are the effects and the relation of being part of the same observable. So a context is just defined by a single observable or single measurement. And a non-contextual hidden variable theory is one that assigns values to each effect independently of which observable they appear in. Okay, so let's start first with this effect perspective, what happens in the ideal case. So each context will be just a measurement, let's say a PVM M with different effects, projective effects PI. And then we want to identify, as we said, different effects, so the same effect in different contexts. So if we take some intuition from quantum mechanics, we will say the two projectors PI and PI prime are the same if they give the same expectation value for all the states rho, So we can promote this intuition to some sort of principle or operational rule for identifying the same effect in different contexts. So we say if you get the same statistics, we are dealing with the same effect. Okay, and this, I mean, in my opinion, is the notion at the basis of measuring non-contextuality introduced by Specken. So it's some operational identification via statistic. Okay, so we have our classical hidden variable theory or ontological model where the probability is given by some distribution depending on the preparation on lambda and some response function depending on the measurement M and the specific outcome K. So we have that if two effects give the same statistic for all possible preparation, then we want to identify them in the classical model. Okay. So via this identification, we can, with this ontological model, we can reproduce the Cochen-Specker type contradiction. So we have this response function and they have values 0 and 1. And if we have, let's say, 3 orthogonal projectors, they will have some, let's say, orthogonality rule, as we've seen before, and some completeness rule. So in this way, one can try to reproduce Cochen-Specker contradiction, this formalism. Okay. There is a problem, however, arising in this way, a problem with the determinism. And what happens in the non-ideal case? Let's say your measurement contains some noise. So then your response function psi will not be in 0, 1. And so we can no longer, in this framework, due to the statistical identification, we can no longer compare the 0, 1 value assignment with this rule. And the sketch, the idea of the proof is relatively simple. So since a noisy effect will be a convex mixture of projectors, or let's say sharp effect, then the statistical identification implies that the same mixture should be present at the hidden variable level. Okay, so then will be a convex mixture of deterministic response functions, so it will no longer be deterministic. Okay, so the conclusion of Speckens was that we cannot experimentally test Cauchy-Specker contradiction with this assumption. So his solution, of course, then was developed also by other people, but the original intuition was to introduce another notion that is of preparation non-contextuality. So we have the identification of effects based on the same statistic for all preparation. And similarly, we have the identification of all preparation if they gave the same statistic for all measurements, let's say, okay? And then, yeah, the hidden variable model, you have that this identification correspond to an identification of the ontological model. So in this way, it's possible to derive other type of non-contextuality inequalities. And this is just one example where they've been tested experimentally, but there are also several other papers that discuss this. This is just to give a general idea. So as you see here, there is no marginal, there is no joint measurement, and so on. This is so a possible, let's say, solution or a possible path, let's say, to test something like contextuality. Okay. So let's go back to this observable perspective to see some, let's say, difference or analogy or difference with this property. So we've seen this also in several other talks, and I also mentioned before. So we have a set of measurement, a set of context, and then this joint observation for each context. And as I said, non-contextuality corresponds to the existence of a global distribution reproducing of these marginals. But in this abstract or mathematical formulation, these contexts are somehow given or maybe identified assuming quantum mechanics. So for instance, in the Cauchy-Specker theorem, we say we have projective orthogonal projectors, or we have commuting operators or something like that. But if we want to do some tests, some experimental tests of classical versus quantum theory, we would like to remove any quantum mechanical assumption. So if we already assume quantum mechanics, we could already rule out classical theory. So what is the point of the experiment? So we would like to kind of remove all possible quantum assumption on, let's say, commuting operator and have some sort of operational definition. So how can we do that? Now, imagine I give you all these measurement boxes, this measurement device, and I ask you, what are the contexts? How can you say that you're measuring a context? How can you say that you're measuring a property of the system? How can you combine them together in some sort of non-contextual way, and so on? So these are all the questions that we should deal with in the lab. Okay. Yeah, some intuition may come from the simplest or let's say the scenario that is most well known, which is the Bell scenario. And here we know that contexts are just a joint measurement of one observable for Alice and one for Bob. So we have some sort of locality assumption. So here, if I use the box A1 here or here, I know that I'm doing the same measurement in two different contexts. So here is together with B1 and here is together with B2. So the notion of context here is more or less clear. The identification of the same measurement in different contexts is also relatively simple. So it's just, I'm using the same box, okay? Yes, and what is the non-contextuality assumption here comes from locality. So the choice of the measurement on B does not influence the outcome of A. Okay, and here we can construct, as we know, the local hidden variable theory and yeah, derive Bell inequalities and so on. So here we have, let's say, a clear operational identification of all this concept, okay? So can we generalize this? Can we have an analogous expression, analogous assumption for different scenarios that do not involve, let's say, space-like separated events? So can we interpret the measurement as black boxes, for instance? What are the physical assumptions? Okay. Again, here to get some intuition on this, we should go back to the ideal case. We kind of pointed to, so not us, but also in the literature, people pointed to main assumption. One is that of repeatable measurement, that this tells you that you're kind of measuring a property of the system, not just a random signal or random outcome that is generated at the moment, but there's something to do with the property that you keep measuring and you always find the same thing. We've seen also yesterday this idea in the talk of Professor Ozawa. There was this idea of kind of repeating measurement and getting the same outcome. And the other things is that we've seen also in the best scenario is the idea of non-disturbance, so that measurement do not influence each other. Not only is a property, or we should try to interpret this as a property, but also they are not disturbed by different measurement. Okay, and from a quantum mechanical perspective, these two assumption kind of recover the idea of the case of ideal commuting projective measurement. So they're sharp, repeatable, non-disturbing, and so on. Okay, and to better understand this, all these different notions, let's talk about a specific example. So in this case is the Peres-Mermin square. So we've seen also in the previous, some of the previous talk, people already mentioned this, but I will just give you brief summary. So we have these 9 variables, okay, and we want to interpret as classical random variable, and we know we have the assumption that they are compatible along rows and columns, so we can perform a measurement of A, B, C, A alpha, and so on. Yes, along these rows and columns, it's possible to measure jointly, and these are the given context, and we want to okay, we assume this value plus or minus 1. So from this assumption, one can derive some this is called non-contextuality inequality, the Peres-Mermin inequality, which has this form where I have the expectation value of all the rows minus the last column, and the classical bound, the non-contextual bound, is 4. We can have a quantum realization of this setup just on a 2-qubit system. So these are, I interpret A as this measurement, B as this measurement, C, and so on. And for this specific realization, we have that also the variable satisfied, because of the way we choose them in quantum theory, they also satisfy this constraint. So their product along rows and columns is always the identity, except the last column in which it is minus the identity. So if we substitute this thing, we find that we can have expectation value 6 for this expression, which violates the classical bound. So I also want to emphasize that this is a specific, so this condition, this identity condition is a specific condition for this realization, but I mean, it's easy for us to calculate this bound, but if we were to obtain, I don't know, 4.5 would still be a valid thing. So it's not necessarily important for the argument, okay? So how do we proceed in an experiment? So this is an example of the Innsbruck experiment of the Peres-Mermin square, but we can have a more abstract representation. So we can measure this in sequence. So we can measure A, B, and C to get the first row, or first row, or A, small a and alpha to get the first column. So we perform all these measurements in sequence, and we can extract the expectation value. Okay, but this is not enough. So if we don't want to assume quantum mechanics, how can we know that these are the right measurement, that we're really that have something to do with context or compatible measurement and so on, without assuming quantum mechanics? So that we have to check these two properties that we mentioned before. So first is a non-disturbance. So the outcome of A is not disturbed by B. So in this case, it's confirmed even if I measure B in between. So let's say for A, I get the first outcome, let's say +1, then I measure B, and then I measure A again, and I get +1. So I can kind of infer that B has not disturbed the value of A. And similarly, I can just measure A alone. I can show that this is somehow some sort of repeatable measurement, okay? I perform the measurement several times and I see that I get the same outcome. And so on, we can do permutation of this. So more variables, longer sequence, permutation of this thing, and so on. But this is just the intuition, so we still need a more detailed classical model to interpret this. Okay, but this is the general idea. Yes, before going forward, I also would like to spend some time to discuss some common misconception about the pairs mean square. So this is something we found in several papers. So I thought would be nice also to clarify this. So first thing is that we don't need assumption. So there are no quantum mechanical assumption needed to define the non-contextual hidden variable model. For instance, that the product of these three variables always +1 is not, I mean, this is something that we found is not necessarily needed, or that the product of AB, which in quantum mechanics is represented by this two operator is equal to C, which is this one, also is something that we don't need, or we can substitute the product of ABC with just the corresponding quantum operator, in this case, the identity. Or another misconception is, for instance, that the sigma x is given by two single qubit measurement with 4 outcomes. So I can just measure sigma x locally in the two and then combine them together. Or, for instance, that I need the assumption of determinism. So just maybe to summarize this, these are somehow all wrong, just to clarify that it's something we don't want to have. So first of all, we don't want to have a quantum mechanical assumption. These two are not needed, and this substitution removes every possible contradiction. And the other hand, the single qubit measurement removes the commutativity of the operator. So if you look at the PVMs, they are no longer non-commuting, and then there is no, if I assume determinism, so I don't need to assume determinism because there is no statistical identification. I get this for free, okay? So people have tried several things to deal with this notion of disturbance, for instance, and this is some sort of incomplete list. I just wanted to, so something that I found interesting is that all these papers deal with disturbance. There is the paper of Liang, Speckens, and Weisman that deal with sharpness, but is a very different framework. We've seen the other day in Shane's talk that he introduced something that some framework that took into account disturbance and sharpness. So I think this would be very interesting because so far it seems to me that there is no, this sharpness is conceptually important, but has never been investigated, let's say, quantitatively. Yes, and this is just to give some example of how the physical assumption of the noise enters here. So in this case, in this particular experiment, and this is more like the theoretical investigation of this problem, the assumption was that of some cumulative noise. So in some sense, the noise effect do not conspire to cancel it. So the more measurement you make, the more noise you introduce in the measurement. And in this way, they were able to take the standard non-contextuality inequality and modify the classical bound to account for the noise by introducing these extra terms that, for instance, the flipping probability, if I measure B, A, and B, what is the probability the outcome is flipped? Okay. Yes, and this is just a summary of the different procedure. I can go relatively fast also because my time is almost over, but basically there are these 4 basic steps if you want to perform an experiment in this framework. So first, define the experimental procedures, then identify the context. So for instance, doing this extra experiment to see whether compatible, repeatable, and so on. Then you perform the measurements in different sequence to extract the statistics. And then you compare these statistics with the prediction of non-contextual variable model. So far will be kind of in the ideal case. So what if the measurements are not ideal? They will introduce some disturbance and we can try to quantify it. So yes, one can try to quantify the deviation from ideal measurement. And there are several models. I gave some example before, but yes, the idea is that there is no general recipe for doing that. You have to, I would say, for each experimental setup, you have to look at it, try to justify why you have this type of physical noise and so on. So this is, I would say, still an open problem, okay? And yes, this brings me to the end of my talk. So just to give you a summary of what I've said so far. So I try to argue in this short time, so it's quite difficult to move from a logical contradiction to experiment. And there are different approaches that somehow have a similar origin from the Cauchy-Specker theorem, but then they developed in very different directions. Okay, I think this is sometimes a source of confusion because people applies the criteria of one approach to the other, and maybe they don't make much sense in this case. Okay, and I also want to emphasize that in many theoretical approaches, the contexts are somehow given, but there is still we still need quite some theoretical work to really understand how to identify them in experiments and how to deal with imperfection in let's say disturbance or sharpness in experiments. I also try to explain this conceptual role of disturbance and sharpness, and also to emphasize there is no general solution. So for each setup, one should introduce a model, should try to justify why this is the correct model, do some extra experimental run to verify their assumptions and so on. There are also some open problems. So in particular, I found very interesting this problem of the role of sharpness in some quantitative way, not only related to the idea of property of the system, but also what the failure of sharpness or in a quantitative way, what does it imply, for instance, for the non-contextuality bound of a certain expression, okay? What is the most general noise model? Can we maybe combine the different approach into a unique and maybe general one that could be applied in most experiments, for instance? And the main open question is whether it's possible to make some reasonable loophole-free experiment. Of course, as in Bell experiment, I think one cannot have a completely loophole-free. There is always some. No, I mean, one can just say that don't believe in random numbers or they believe in faster than light communication. But I would say for contextuality, as for Bell inequalities, maybe it's possible to devise some sort of reasonable loophole-free experiment. And I think this is a very interesting question that we should investigate in the future. And yes, with this, I'm done. So I would like to thank you for your attention.
I have a question about the motivation for this. In other words, quantum mechanics is well established, agrees with all the experiments. Every attempt to replace it with classical physics fails in the quantum domain.
Mm-hmm.
Why do we need more experiments? It's as if we were trying to check special relativity with experiments, but everybody accepts it. So why are experiments needed in this domain?
Well, I think it's, I think this, so the quantum contextuality highlight this, this contrast, this tension between the idea that a quantum measurement just reveals some predetermined effect or some predetermined value, and then the prediction of quantum mechanics. So there is some contradiction there, and I think as long as you, so that I would say is not completely satisfactory as long as you have some sort of loophole or some sort of easy and cheap explanation, just some disturbance, right? So you can have some sort of, I don't know, Heisenberg microscope argument that just, the measurement of position disturbs the momentum of your particle, but this is not, it seems to me that this is not a satisfactory explanation, because if you, it will be the same also for, let's say, Bell inequalities. You will have to assume that either there is no randomness in the universe or that you have faster than light communication. So if you can really close the door to all these possible, let's say, cheap explanation, because in contextuality experiments sometimes are like very cheap explanation. You don't have to call into, I don't know, faster than light communication, things like that. I think it's still an interesting interesting question. So I think nobody expects this. So you mentioned that we don't need to verify quantum mechanics because we know to be true. I think nobody expects the prediction of quantum mechanics to turn out to be false in this setup, but I think it's still interesting, it's still a challenge to this experiment.